And we're back. I don't think I had a whole second on that one. Oh, I forgot I had another device. Never carried one like this. I like them. They're really good. This is a great calculator for using a sling psychrometer. The problem with it, they're great to have in your truck. They're too big to fold up, and they don't fold up. They're too big to stick in your little belt pouch or something like that. But they're a lot easier to use and easier to get used to than that chart I showed in the previous segment. Precipitation. This one's challenging. How do you measure precipitation? The only one that's easy to measure in a relative sense is rain. There's these open tube ruler type gauges, and maybe it's got a really big funnel at the top and then a smaller tube. All that does is it makes the ruler kind of stretch out because I've got a large area for collecting in a small tube. So 1 inch of rain might be 4 inches or 8 inches or 12 inches in the tube. What I like about those things, I have one like that in my backyard, and I can actually look from 50 feet away and look over after a rain in the morning and see approximately where I am without even walking up to the thing. And it also helps make a more accurate measure. If you have just an open top tube, it's really hard to get a really accurate measure, especially for small amounts of rainfall. You've got a big collector in a small tube, then it fills up that tube much, much faster, and you get a longer column of water to measure, which makes it more accurate. But that also means you have to be there every single day, multiple times a day, perhaps, measuring how much is in the tube and dumping it out. That's not practical. So they have what are called tipping bucket meters, and that's what we have here at the bottom. And there's literally a piece of pipe with a divider down the middle. And what happens, if you imagine the divider here, it tips to one side. And when it tips to one side, the water comes in to this little V that's formed and fills up because it's not just a V, it also has sides on it. And as that little V with sides on it, that little cup shape fills up, it'll get heavier and heavier and heavier until finally it goes tip and it pours out the water. And now you have a new cup pointing up. And it starts filling up until it gets heavier and heavier and heavier, and tip, it pours its water out. And it can tip back and forth without anybody being there and have just a tiny electronic gauge that just measures how many tips. And with a well-designed device, you can know exactly how many milliliters of water each tip represents. And very, very accurate. They work wonders. But there are all kinds of things that go wrong. Ants and spiders and other insects can get in here and mess up things. Spiders build their webs and the water runs off the side rather than into the bucket, or doesn't even go into the device at all. Ants love electronic things, so if there's much electricity that they can sense, ants can get in there and mess with the electronics. Um, and if it starts hailing, these things don't do very well in hail. They really don't do very well in snow. Um, Freezing rain, So you need other ways to deal with the really cold types of precipitation, snow, hail, freezing rain, things like that, sleet. But the typical rain events and weather that we have in most of California, most of the time, these things work wonders. Most of agricultural California, I should say. So the tipping bucket gauge is fabulous, and you just can measure it in inches per day, inches per hour, or millimeters. It's always a distance, assuming that it's covering an entire area. It's not about gallons, because are you talking about one potted plant or a 100-acre field? So it's how many inches of water fell on that region? Or in metric, how many millimeters of water fell on a given region? As I mentioned, snowfall's tricky. And so how much snow falls? You need to have different kinds of experience and measuring devices. Snow builds up in piles or drifts with the wind. So if you measure it in one area, you might say, wow, we got 8 feet of snow. And in another area, we got only 6 inches of snow, because wind can blow the snow away from some areas and it accumulates and drifts in others. So you really do need to have a good measuring stick, a good knowledge of the terrain and how snow accumulates. And it takes some experience and practice and multiple measures to average out what you think it really is. But it's not just how deep the snow is. That's only one measure. It's also how many pounds per foot of snow in a given area. You need to take cores of the snow and see how much water is actually there. I can have 1 foot of snow with more water in it than a very light, fluffy 6 feet of snow. I could have a very wet, heavy, dense 1 foot of snow holding way more water than a powdery, light fluff. So when the snow measurers are out there, they are measuring not only how deep it is, because that's one measure that's important, but how heavy it is. And that literally, it's not so much how heavy it is that they're really concerned about, how much water does that snow represent. And so they will calculate it. Well, we had 4 feet of snow, which came out to be, 4 inches of water, 2 inches of water. And that also, not only is it important for measuring the snow, it's also important for planning what we're going to do about water for droughts and irrigation water later. If you're getting water from a well, that snowpack might mean recharging the well where you're pulling water out. If you're getting water from a reservoir, that reservoir very likely has significant amounts of snowpack that hopefully melts over many months in the spring and early summer to fill up your reservoirs for irrigation and home use and everything else. So, next topic, clouds. Meteorologists monitor clouds in several ways. There's how much of the sky do they cover? What kinds of clouds are they? Cirrus, cumulus, stratus, etc. They mean different things. How high are they? Are they clouds that just maybe block a little bit of sun but don't have any weather events associated with them? Or are they like a major thunderstorm like the cumulonimbus clouds, our thunderhead clouds? Very important to know what is going on. So we talk about the different levels of clouds. The low, medium, and high altitude clouds are grouped together in groups. And in which direction are they moving, which might not be the same as the ground wind direction. And that can be kind of mind-blowing at times when you're looking at the wind and the wind's blowing whoosh in this direction, and you look at the clouds and they're going that way. Well, we have layers of air movement, almost like skin of an onion going over the earth, and the atmosphere is in these different layers. And you get a lot of turbulence between the layers as they move across each other, but they definitely move in independent ways that often don't take into consideration at all or have any influence at all, really, what's going on above or below that particular layer. Don't worry about memorizing the clouds. The cumulus are the fluffy clouds. The cirrus, the high feathery clouds. Stratus are flat clouds. And if we get stratus at the ground level, we call it fog. Fog can form on the ocean and come in as low stratus. and you can actually develop ground fog with moisture that comes up and creates uh, a very high humidity layer over a moist soil. It happens in the Central Valley of California every year. We call it the Tule fog because the areas with lots of moisture where you might find tule plants growing, those moist areas build up a lot of moisture in the air, and then overnight it gets cold, and so that humid air just turns into a ground fog stratus cloud right there on the ground. Very, very dangerous when it happens on I-5 or something like that. All right, next, evapotranspiration. This is one where I really wish I had um, you guys in class and we could talk about it, get some back and forth, draw some pictures on the board. I just think this is one you really need to wrap your heads around. Evapotranspiration is the loss of moisture from the soil. And it is lost in two ways. Evaporation, E, which is water coming directly from the surface of the soil through the processes of the sunlight, the heat from the air, and wind movement. And then transpiration, which we already talked about, is the water that comes directly through the plant, out of the soil, into the plant, and is evaporation from the stomata on the underside of the leaves. And a combination of evaporation and transpiration is evapotranspiration. And we also have water going back into the soil, which is precipitation events. So that would be a negative evapotranspiration event where water's going back in, as would an irrigation event. So if we on purpose ran sprinklers or drip irrigation or whatever, that would be a negative evapotranspiration event. And we measure ET in inches or millimeters of water lost in a given area. And it's a relatively simple calculation that you can do based on various mathematical models. Now, hopefully this isn't the first time you're hearing about it, but if it is, do a little reading up about it, look into it. It's important to know. We go into it more in damn near every class I teach. We talk about evapotranspiration and all of the production related or science related classes because it is that important. So how do you actually measure it? ET is measured with a device called a lysimeter, and this is a giant canister that's in the soil to experience the same weather conditions as the soil with the same plants. Very expensive, very challenging to run a good lysimeter. I've only seen them used for university studies. I've never seen an ag person make a lysimeter. They do it all now through weather station data. But you can use lysimeters for all kinds of research if you're a company that is interested in doing your crop research or primarily universities. Water balance with your plants, water infiltration with different soils and irrigation methods, water drainage with your soils and different crop types, dry matter accumulation, because as you're growing crops, you're not just using water, but you're converting carbon dioxide in the air into plant material. And fertilizers that you add are being turned into plant material. And that plant material is mostly water, but it also is 4, 5, 10% other dry matter, the non-water solids that make up the plants that grow. They add to the weight or mass. So in order to measure ET, there can be experimental data or mathematical data. And I'll show you, well, right here we have the numbers that go into the mathematical calculation. But the only reason we have these mathematical calculations is because people spent decades and decades and hundreds of experiments in dozens and dozens of universities around the world playing with lysimeters to come up with mathematical models that farmers can use. So farmers don't have to do this work. They can all do it based on weather data and math. And so you need the air temperature. That's really important in water loss. Soil temperature, that's also important, warm soil versus cool soil. The relative humidity, remember the wet, high relative humidity air will not accept much evaporation or transpiration, but dry air, evaporation goes faster, transpiration goes faster. Solar radiation, a measure of how much the sunlight is hitting the plants or the soil. And rather than a farmer worrying about cloud cover and the percent cloud cover, sometimes they just look at solar radiation. It's an easier thing to look at because if you have a thin overcast or you have a low sun in the sky during the late season in the fall or something, the solar radiation will take that into account. And you just need to know how much sun is hitting my plants. That's the bottom line. Whether it's because of the angle of the sun, whether it's because of uh, shade from cloud cover, doesn't matter. Wind speed and precipitation. Remember, precipitation is putting water back. You also need your irrigation events as well. So here's a picture or a diagram of a lysimeter in profile. Here's that canister that I told you about filled with soil and some soil moisture probes. I'm sure there's a temperature probe in there, etc. It's on some sort of a scale or balance to measure the mass of the soil. There's drains in here. There's usually going to be an access door, possibly even a little computer workstation down here. You don't work there all the time, but there would be, you go through the cover down below and you gather your data, come back out. You don't work down there all day, but that is a lysimeter. And you'll notice it says ETO, experiment station. ETO stands for a standard grass. And then you have to adjust that because if I have all of the same conditions, I have the same temperature, humidity, wind speed, solar radiation, all of those factors on a field of alfalfa or a field of grass or a field of lettuce or an orchard of grape vines, I'm going to lose different amounts of water. Different plants are going to have different evapotranspiration. So we always have a standard. ETO is standard grass. ETA is standard alfalfa. And everybody else adjusts from there. You either start with a standard grass and say, well, my crop uses more water, so I'm going to bump it up for a certain percentage compared to a standard grass, or whatever. You adjust the standard. So the standard is ETO based on a standard grass, ETA for alfalfa. Your crop ET is called ETC, evapotranspiration for your crop. So for example, if my evapotranspiration for grass this week was 1 inch, I lost 1 inch of water this week, I would have to multiply that times what's called a crop coefficient or some adjuster. And maybe my crop adjuster is 0.8. So grass lost 1 inch, but I multiplied my crop times 0.8, so my crop lost 0.8 of an inch. Or maybe my crop uses more than grass. So if grass was 1 inch and my crop coefficient, my adjustment is 1.2. Well, grass lost 1 inch. My crop lost 1.2 inches. You adjust it. But it's not simple. I can't just say, well, I got lettuce. What's the adjustment for lettuce? It is based on the crop, but I also need to know the growth stage of the crop. Is it lettuce plants that are the size of a dime, or is it lettuce plants that are, head lettuce that's about ready to harvest, or somewhere in between? So the stage of the crop also adjusts your evapotranspiration. And you look at the percentage of soil. If you imagine looking from above, how much is crop and how much do you see as soil? And that helps you determine the evapotranspiration for your crop, ETC. So here's another lysimeter experiment, an ETC experiment station. The ETO experiment station had grass growing on it. The ETC experiment station has a specific crop. In this case, it's an entire, I don't know, orange tree or peach tree. And so you can see this one has an access as well as a computer station, and a very complicated, expensive, tedious experiment to run. So you can get your evapotranspiration number based on the weather data, based on grass or alfalfa if you're in a different part of the country. We have something called the California Irrigation Management Information System. California Irrigation Management Information System, or CIMMYS. And we'll talk about that later, but CIMMYS allows you to pull up evapotranspiration at different points in agricultural regions throughout California. So you don't even know have to know how the math works to get ETO. Gives it to you for you. And once you have ETO, then the hard part comes and some decision. You have to come up with, what is the K crop? What is my adjustment I need to do to go from grass to my crop at my stage of growth? And this is where experience and knowledge come in. You got to pick the right K crop, and there's no magic bullet for that, but there's lots of papers on it, lots of experience. It's something that you warm up to after you've done it for a while. So you take your grass number, you multiply it times your adjuster. That adjuster, like I said, could be 0.8, could be 0.92, could be 1.1, whatever your water loss is calculated. If you are growing grass, you multiply it times your K crop to bump it up or down a little bit, and that gives you your estimated water loss, or ET crop, for your situation for water loss today or this week or whatever period you're looking at. So here's a crop coefficient curve for a particular crop, and they're all going to look different. So here's some actual K crop data that's been measured and the approximate numbers based on the crop development stage. Is it the initial stage? Is it in the development stage, mid-season stage, late season stage? And they all look similar, but they can have different shapes and certainly different angles. So you need a crop coefficient graph that works for you. And on this basal crop coefficient, there would be actual numbers here. And you'd have to say, where am I today? Well, based on my knowledge of my crop, I'm right about here at the later stages of crop development. And so my K crop is 1.1. But in a little bit, it's going to be 1.2 as soon as I reach this plateau. Got to pick up good K crop data, or all of this ETO stuff doesn't do you much good. Here's another crop coefficient one with actual data. And days after planting on a particular crop in a particular area. This is a cowpea somewhere in California. It doesn't matter. This is just actual measured data and the estimated K crop values. And based on your days after planting, you just go, all right, mine is right here at 50 days, so we're at 1.1. And with more experience on your varieties and your soil types and other things, you can even say, yeah, it's 1.1, but with this variety or this soil or whatever, I'm going to call it 1.2, even though this says 1.1. That's where your experience and your knowledge of your varieties, or your knowledge of your fields, comes in handy. You can tweak the K crop to give you the best possible information for your water use estimates. And that's it for weather and the basics of evapotranspiration.